So last time, we got our build and deployment pipeline working. But every time we push new changes, the task gets a new IP address. Today we're fixing that. And by the end of this video, you'll have one stable URL that never changes, no matter how many times you deploy. So here's what we have right now. GitHub Actions builds our image, pushes and stores it to ECR. And then it spins up a new task definition, which we tell ECS to use. The task gets a new public IP on every new instance, which gets a little annoying when you have to update the user for the new address every single time. We have a very easy fix. We put a load balancer in front of the tasks. But to make that work, we need three things wired together correctly: a target group, a listener, and the load balancer itself. The target group keeps track of which tasks are healthy and ready to receive traffic. The listener is the rule that says, when someone hits a port, say port 80, send them to the target group. And the load balancer is what sits on the public internet and makes all of it reachable. Okay, let's get into the code. So here's our current workflow. We got one job and a handful of steps. This works well, but it's doing too many things in one place. The first thing I want to do is clean it up. Separate the concerns into their own named steps so it's obvious what's happening at each stage. You'll see I kept the structure you already know. We're not rewriting anything from scratch, we're adding onto it. Right, so first is the build and push. This step doesn't change. We build the image, we push it to ECR, move on. Next is a new step. Before we can create a load balancer, we need to know which network to put it in, and specifically which subnets are available. So we grab the default VPC first. Every AWS account comes with one. Then we ask AWS to list all the default subnets inside it. Now, we're not just grabbing one subnet, we're grabbing all of them. The load balancer has a hard requirement. It needs to span at least two availability zones. That means at least two subnets in different AZs. If you only give it one, AWS will reject the request outright. We'll look them up dynamically instead of hard coding them. Next is another new step where we handle security groups. This step handles two groups, one for the load balancer and one for the ECS tasks. You'll notice we always check if a group already exists before creating it. This makes it idempotent. It's safe to run on every deploy without creating duplicates. If it exists, grab the ID and move on. If it doesn't, then we create it. The first security group is the public-facing one. It belongs to the load balancer, and it allows HTTP traffic on port 80 from anywhere on the internet. The whole point of this load balancer is to be publicly reachable. The second one is quite interesting. Instead of opening port 5000 to the internet, we set the source as the load balancer security group. What that means in practice, the only thing allowed to talk to your containers is the load balancer. Not a specific ID, not a CIDR range, literally only traffic that came through the load balancer. Your containers are never directly exposed to the internet. The load balancer is the only door. Another new step is for the things I mentioned to make the load balancer work. This step has three parts. They build on each other, so the order matters. So first is the target group. This is how the load balancer tracks which containers are healthy and ready. We tell it which port our app listens on, which VPC it lives in, and how to check if a container is ready. In our case, a GET request of this route that has to succeed twice before traffic is sent to it. Second is the load balancer. We pass in all the subnets from step 2, that's why we grabbed all of them, not just one. The load balancer needs to span multiple availability zones, and each subnet represents one zone. We also pass in two other things. The security group from step 3, which allows port 80 traffic from the internet to reach it, and setting the scheme to internet facing, which tells AWS to give it a public DNS name rather than keeping it internal. Lastly is the listener. It tells the load balancer when traffic arrives on port 80, then forwards it to the target group. Without it, the load balancer and the target group both exist but have no idea about each other. At the end of this step, we grab the load balancer's DNS name, save it as an environment variable. We'll print it at the very end of the workflow. That's the URL you'll give out to your clients. It doesn't change when you deploy. It doesn't change when your task restarts. It stays the same as long as the load balancer exists. Now in the next step, register task definition. You know this one from the last time. Every deploy registers a new revision. AWS keeps the full history. That means if something breaks, you can always roll back to a previous version. So, same pattern as before. Check if the service is active, update if it is, create if it isn't. But there's one critical change in the create path, the load balancer flag. This is what wires the ECS service to the target group we created in step 4. Once this step runs, the service is live, the load balancer is connected, and the traffic has a clear path from the internet all the way to your container. Everything we set up in the previous step is now working together. And lastly, the verify deployment. We wait for the service to stabilize, meaning all desired tasks are running and passing their health checks. The workflow just sits here until it gets a green signal. This matters more than it looks. Without this way, the workflow would print success the moment the deploy command was sent, even if the container is still starting up or silently crashing in the background. And once it's stable, we print the URL. The same URL every time. No more digging through the console for a new IP after every deploy. That's it. That's the whole workflow. So here's what we built. GitHub Actions handles the full pipeline. ECR stores the image. The task definition describes the container. The ECS service keeps it running. And the load balancer gives a permanent address. So these 5 moving pieces, each one has a job. Each one depends on the ones before it. Once you see how they connect, the commands start to make sense on their own. Alright, cool. So I hope you learned something new today.